Hi everyone, let's go through a bit of week 7 probability, multi-stage experiments. It's a pretty bad name for the lecture because we actually started multi-stage experiments last week, but we continue with them. And the difference with last week and this week is, this week you can see down here, we've got some probabilities drawn on the arms of the tree diagrams. So last week it was much simpler. Maybe I did something that was 50-50. This could happen, A could happen, or B could happen. Then I did it again. A could happen, B could happen, A could happen, B could happen. And the arms were unlabelled, meaning they were just equal probability of each one happening. I could have, if I wanted, labelled it a half and half, but if they're unlabelled, it just means equal. Even if there were 3 things, it means it's a third, a third, a third. So, you know, maybe that's a tree diagram from last week, and whatever was going on at the end of each let me just finish writing this. A, B, C, can't multitask. The probability of A happening was the same as probability of A, B. All of these final outcomes, in its case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, were all equal in likelihood. They're all 1 in 12, 1 in 12, 1 in 12, so on. The difference this week is, look at these final outcomes. They're not all the same because it's a weighted tree diagram. Okay. It's not just equal probability on every arm. So let's delete that scribble and say, well, okay, this example. Because Scott is an unscrupulous character, he always carries around a biased coin which comes down heads 2/3 of the time. So instantly we see I've got 2/3 probability of getting a head and 1/3 of getting a tail. Now, this is also space saving and time saving. I mean, something could happen to say, look, I've got a barrel. Maybe I've got 5 black balls in there and 15 white balls. Okay, I'm going to select one out of the barrel. Who wants to do 1, 2, 3, 4, 5 and put B's here? And then 15 and put W's there? Well, we could, and each outcome would be equally likely. But what's easier, doing that or just saying, look, there's only 2 different outcomes, black or white. I've got a 5 in an overall 20 chance of getting black. I've got a 15 in overall 20 chance of white. Okay, so that's what we're doing. It's much easier, so we can represent a biased event by putting our probabilities on the arms. Note here, 5 on 20. I could have written 1/4 and 3/4 here. Whether fractions are simplified or not isn't quite relevant in probability. It's the same fraction, simplified or not. So, we're going to put probabilities on the arms. Now let's look at this case here. I've got a 2/3 chance of heads and a 1/3 chance of tails. Fantastic. Say hypothetically heads did happen. I've then still got a 2/3 chance of tossing another head and a 1/3 chance of tail. The tossing of the coin first time round, the outcome of that doesn't affect the tossing of the coin the second time round. Okay, independent of each other. And again, of course, I could have gotten a tail and then tossed the coin, and they're all the same. So really I've got 3 duplicates there. Now, when we read the tree diagram, we go back to the thing we finished off with last week, which was a multiplication principle. So it goes back to, like last week we were saying something or something else, that's a plus in probability. The probability of this happening or this, you add the 2 together. We also ended in this multiplication when we said if it's probability of this and probability of this, it's a times. So that's what we're going to go with. The probability of getting this head is 2/3. The probability of getting a head again is 2/3. The probability of getting a head and then another head is 2/3 times 2/3, which is 4/9. Yep. In the same way, getting a head then a tail was a 2/3 times the 1/3. So you just walk across along the arms and just multiply the probabilities of that happening and then that happening. A third and then 2/3, a third and then third. Let's look at what we end up with. We've got a 4/9 chance of head then head, 2/9 of head then tail, 2/9 of tail then head, and 1/9 of tail then tail. We should do a check as well, check our own calculations to make sure this is a list of all things that could possibly happen. I mean, here's the outcomes, otherwise known as the sample space. I could get head, 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 tail, tail, head, or tail, tail. And the probability of all of them happening must add up to 1. 4/9 and 2/9 are 6/9. 7, 8/9, we'll add 2 more. Plus 1/9 is 9/9. That's 1. Perfect. Also note that the probabilities along each arm has got to add up to 1. Like, if it's only split into 2 bits, the 2/3 and 1/3 must add up to 1, as they do. If I had, say, a 3-pronged thing of getting A, B, or C, and I told you I had a chance of 2/7 of that happening and 1/7 of that happening, the probability of the other one must be 4/7. If this lists all the things can happen, 2/7, 3/7 plus 4/7 is 7/7. All of the arms probabilities must add up to 1. So there's a bit of a self-check there. So in answering the question from the one we just looked at, the question said, was there a question? If he tosses his coin twice in a row, the tree dog represents it. There wasn't a question. Let's make up a question. Okay, what is the probability of using Scott's coin and getting a head and then a tail? Remember this from last week? Probably head tail was literally head and then a tail. So that's that one. Here's tail and then a head. And so if I said, what's the probability of getting one of each? Well, that's saying, I don't care the order. One of each is meaning a head, tail, or tail, head. And what do we say for or? Or was plus. I'd say, well, it's 2/9 of probability. I'll write it out properly. The probability of head, tail, or the probability of tail, head would equal 2/9 plus tail, head, which is 2/9, which is 4/9. Okay, and so on. Next one. Okay, here we're doing a card. Now what's the difference here? The difference here is the outcome of the first happening affects the second happening. Here the happening is us drawing a card. Because we're not replacing, it says without replacing the first card, we go up to a full pack and take a card out. Fine. Maybe I want to know what's the probability, let's make up a question. What's the probability of selecting 2 cards and getting an ace, then an ace? Well, the probability of getting an ace out of a pack of cards, there's 4 aces out of 52. Then if we say it's without replacing the card, it means I leave that card on the bench. Now, considering that I did pick an ace, what's the chance of getting another ace? Well, now there's only 3 aces in the pack, and there's only 51 total cards in the pack, because one of the aces didn't go back in the pack. If I asked the same question, and the question said, with replacement, in other words, take the card out, look at it, put it back in, shuffle, then take another one, well, that stays the same. Probably of an ace and an ace, the probability of getting an ace out of the pack of cards is 4 out of 52. Look at it, put it back in and shuffle. There's still 4 aces in there. There's still 52 options. So either way, that's our multiplication happening. But we've just got to check in the wording of the question, does that denominator change? Does the numerator change? Okay. So in the question we're looking at here, delete. We're looking at without replacement. So we're trying to find, well, we're trying to pick out, just split the cards into red and black. And the question says, what's the chance of choosing 1 card of each colour? So we're going to select 2 cards without replacement. Firstly, let's pick our first card. Underneath there it says, well, I've got 26 red cards out of 52, so chance of red is 26 on 52. There's also 26 black cards out of 52, so we've got even chance. I could have just written half and half. To be honest, I could have written nothing if I wanted, because it's an even chance each way. So I've left it unsimplified just to say there's a total 26 on 52. Fair enough. Now when I go to pull out the second card, notice all the denominators are only 51 now, because there's a card missing. And as for the numerators, there were 26 red cards. I got one, so now there's only 25. There were still 26 black cards in the pack, because no one took one out. And let's check our addition. 26 on 52 plus 26 on 52 is 52 on 52. So that's 1. What happened here? 25 on 51 plus 26 on 51 is 51 on 51. Again, all these little branches are adding up to the number 1. Down here, if I picked out a black card, now there's only 25 black cards out of a total of 51, but there's still a full complement of 26 black cards out of a total of 51. And then we do our multiplications along the arms, and we get these probabilities. This one's symmetrical. You can see those 2 probabilities are the same and those 2 probabilities are the same. Okay, that will happen. What do we care about in the answer here? Well, it's like the question I made up on the previous page. It just says, what's the chance of choosing one card of each colour? It didn't mean it had to be red then black, or it had to be black then red. It just meant, what's, either way, what's the probability of ending up with a red and a black? So we'll say, well, it's this, or it's this. And like I said with or, it's a plus. And that plus that is 26 on 51. Slightly greater than 50% chance of just ending up with one of each. Great. The next section is conditional probability, which is the downfall of many. I'm not saying it's because it's hard, it's just reading the question carefully. Now, let's just go straight into this question because it's best to explain while doing an example. Firstly, let's check out that this Venn diagram makes sense. It's already been done for us, but let's just check it. In a sample of 250 children, okay, that plus that plus that, okay, my four numbers do add up to 250. 119 have been vaccinated against mumps. So the mumps circle, the vaccination circle, V, contains 119. 14 plus 105, yep, the V circle contains 119 people. 74 have contracted mumps. My M circle, 60 plus 14, does contain 74 mumps people. And 14 have been vaccinated against mumps and did contract mumps. So 14 in the middle are part of the V circle of vaccinated children, and they're also part of the M circle of children who got mumps. The 71 has been calculated by taking the total of this away from 250. Alright, love the Venn diagram. What is so conditional probability about question A? Conditional probability questions are they're giving you a little bit of info in the question. And that bit of info here is, what is a probability that a vaccinated child catches mumps? That is not asked in the question. If I pick one of these people at random, one of these 250 people, what's the probability that they caught mumps? Well, the answer to that question would be mumps is 74 over a total of 250. But read the question carefully. What's the probability that a vaccinated child, as in, I'm only talking about vaccinated children. How many children are vaccinated? 119. So it's saying out of these 119 people, what's the chance of randomly selecting one of those 119 children and they got mumps? Well, let's look. Here's the 119 children in the V circle. 14 of them got mumps. That's the answer to that question. Didn't ask me about anyone else except what is the probability that a vaccinated child, in other words, what's the probability that one of these 119 children got mumps? Well, 14 out of the 119 got mumps. Similarly, the second question. What is the probability that an unvaccinated child catches mumps? We're only talking about the unvaccinated. If V contains all of the vaccinated children, the unvaccinated children must be everything else. What have we got? Everything else, 60 and 71, well, that's 131. So out of those 131 unvaccinated children, how many of them got mumps? Well, 60. Out of these 131, 60 got mumps, 71 didn't. So 60 on 131. There's my conditional probability. So the way I like to think it is, conditional probability changes your denominator. We're talking about only a section of the universal set, not the full universal set. How do you tell that the question is conditional probability? It tells you, it's in the wording. It's just if you read it quickly you can miss it. But this clearly said, what's the probability that a vaccinated child? This one said that an unvaccinated child. It's exactly what it said. I'll do one of the examples because I think we only got one example here. I'll grab some examples at the end of this because it's a fairly short set of course notes, but we'll do some more examples. So there's a quick intro to conditional probability. We'll do some more. But we also need to look at contingency or two-way tables. So we're not finished with the other stuff. This is just contingency tables. I can't talk today. You can use them instead of tree diagrams, okay? Now it depends on the situation, but they're just another way to represent data. Within this contingency table, we can still get conditional probability questions, and we'll see soon that E and F are more examples of conditional probability. But let's look at the table and then we'll work out what questions are conditional, or why E and F I say are conditional and why the others aren't. So the info says, and it's the same info as before, instead of a Venn diagram or a tree diagram, we're just putting it in this two-way table, contingency table. It says there are 250 children, got a total of 250. 119 were vaccinated against mumps, there are those vaccinated ones, total of 119. 74 contracted mumps, here's the mumps column, totaling 74. 14 were vaccinated yet contracted mumps, so 14 were vaccinated and did contract mumps, right there. And you can see, even given only those four numbers, we were able to complete the table, because 14 plus what gives 119? 105. 14 plus what gives 74? 60. 119 plus this. You can see you can do totals everywhere. So we'll grab an example soon where it's incomplete and we'll complete it. But let's look at these statements. From the table we can see that for a child chosen at random, the probability the child had been vaccinated is 119 on 250. Because it's not conditional, it's just saying, it's like the question to that would be, what's the probability of choosing a child that had been vaccinated? Well, there are 250 children. The total, there are vaccinated people who had mumps and vaccinated people who didn't get mumps. Don't care. I just want to know the total that were vaccinated. That's why we've got 119 on 250. In the same way, the second question is just taking a child at random from the whole group. What's the probability the child did not get mumps? I don't care whether they're vaccinated or not. My question doesn't ask that. What's the chance they did not get mumps? 105 didn't get mumps. These 71 didn't get mumps. A total of 176 did not get mumps. The probability the child had been vaccinated and did get mumps, well, choose one child here from random that they had been vaccinated here and they did get mumps, which is here. Well, that's my 14 out of my 250. So hopefully that makes sense. Let's get rid of some scribble. Question D, the probability that the child chosen at random had not been vaccinated, and got mumps. 60 of them. Out of how many? 250. Now, what makes the next bit conditional? The probability that a vaccinated child catches mumps. Okay. If we're only talking about vaccinated children, how many are there? Vaccinated children, there's 119. Out of 119, how many of them caught mumps? 14 of them got mumps, 105 didn't. 14 of them got mumps. That's why that's there. And then the probability that an unvaccinated child, alright, we're only talking unvaccinated, which had a total of 131, so my denominator is 131. And how many of them caught mumps? Well, 60 caught mumps, 71 didn't, so it was a 60. So there's us answering the questions using a two-way table instead of our Venn diagram. Alright, again, that was quick. Let's grab an example to play with. For all of them, weighted tree diagram, which one? I'll just choose 8. Now, a raffle with 2 prizes to be won is held at the local school and 25 tickets are sold. If Sue buys 3 tickets, what is the probability that? We've got a few things. Now, I remember I saw this first years ago, and I remember thinking, hang on, which prize is drawn first? Is it the ticket gets first prize and then the second ticket gets second prize, or is the first ticket gets second and the second gets the first? It doesn't matter. You can draw the tree diagrams. It makes no difference. It also checks, you also want to know is, are the tickets put back in the box? And actually I think this is poor in the way that this doesn't tell us. I'm just going to go off life experience. In my experience of raffles, you don't get your ticket back in the box. Okay, once your ticket's drawn out, that's it. If you buy 1 ticket, you're not in with a shot for 2 prizes. Okay, so hopefully you've been to some raffles. I would hope that in an exam situation we would have been clearer with that to cater for those who are maybe not raffle experienced. So the raffle with 2 prizes to be won is held there, and Sue buys 3 tickets. So let's look at, now Sue buys 3 tickets. I'm going to start out with a tree diagram, but I'm not going to do 3 arms on the first thing. I was going to say And look, it doesn't matter again. Let's say that the first ticket drawn from the box wins first prize. Now, what are the two outcomes that could happen? She could win, or she could, I'm just going to write lose, as in not win. Yeah, fine, win, lose. Now, is it 50-50? Let's look at it. She's got 3 tickets, and there's only 25 tickets sold. So she's got a 3 in 25. She's got 3 tickets out of those 25 sitting in the box waiting to be picked. Lose, well, how many tickets are losing for her? 22 of the tickets aren't hers. And of course they've got to add up to number 1, which is 25 out of 25. So she's got 3 out of 25 chance of winning and 22 out of 25 chance of losing from the first prize. Alright, one of those two things happened. Now let's do the second draw for the second prize. We've still got a win, lose, and we've still got a win, lose. Now, if in an alternate universe they put tickets back into raffles, I would write the same probabilities on all the arms. But we don't. We just don't. She had 3 tickets in the draw. If she won the first prize, that means that ticket got taken out, scrunched up and thrown away. She's now only got 2 tickets left in there. 2 out of how many? Well, there's only 24 left. So she's got 2 tickets left in the box, and there's only 24 tickets left in the box. How many losing tickets are still in there? There's still 22 losing tickets. As in, 22 tickets are not hers. We didn't take anyone else's out, so there's still 22 of them in there. And of course, the 2 on 24 and the 22 on 24 have to add up to 1, which they do. What if she did not win the first prize? That means she's still got 3 tickets in the barrel, untouched, even though there's only 24 tickets left in the barrel, because someone else's ticket got pulled out and thrown away. So she no longer has 22 losing tickets in the box. One of them someone else just won something. There's only 21 opposition tickets left in the box out of the 24. Do 3 on 24 and 21 on 24 add up to 1? They do. So there's my tree diagram. And then I could, I'm not running out of room, but I would put a win-win. She could win both. A win-lose, win one, not the other. Lose-win, win the other, but not this one. And lose-lose. And the probability of all of them is what I get if I multiply these out. 2 by 3 is 6. What's 24 by 25? Well, 4 25s is 100, so that's going to be 600. 6 on 600, 3 22s is 66 on 600. 3 22s is 66 on 600. And what's 21 times 22? Well, 20 times 22 is 440, plus another 21, plus another 22, sorry, is 462. Now I also want to do my check. Do they all add up to 600 on 600? Let's just add up the tops. We've got 66 and 66, well, that's 132, plus 6 is 138, plus 462 is 600. Okay, I'm happy. And look, I might have gone over the top. I might not have had to have written all that out in order to answer the questions. I was just carried away and having too much fun to stop. What is the probability that Sue wins first prize? Well, again, I promise you, write it out, do all this again, and if you write second prize here and first prize here, all of the outcomes work out the same. It makes no difference which way you write it. So the Sue winning first prize in my stuff was only this. Who cares what happens after that? She had a 3 in 25 chance of winning first prize. Okay, I promise you it's true. 3 tickets, she had a chance, and then the other chance, the other probability was she loses. So all I can go is Sue winning first prize is 3 out of 25. Hey, look, there's other ways to approach it. Let's just keep it simple. 3 chances. If she didn't win it, there's no second chance of winning first prize. It's gone. B, Sue wins only 1 prize. Well, here's Sue winning 1 prize, winning the first one, but not second prize. Here's Sue not winning second prize, but first prize, but winning second prize. It's the sum of those two. Sue winning only 1 prize is either win-loss or loss-win. So it's these two added together, or is a plus. 66 plus 66 is 132 on 600. Question C says Sue wins no prizes. That's lose-lose. 462 on 600. these probabilities aren't simplified. Okay, you can simplify them, it doesn't matter. And Sue wins at least one prize. These questions at least and at most can be little traps, but just approach them with common sense. Sue wins at least one prize. That means, yes, she gets, I'll just box it. Here's Sue winning at least one prize. Here's Sue winning at least one prize. Oi, back. Here's Sue winning 2, that's at least 1. So I can either add up these 3, or I can just do 1 minus this one. What's the opposite of her winning at least one prize? The opposite is her winning nothing at all. So either add up 66, 66, and 6 to give you 138 on 600, or say the answer is 1 minus this answer, which is still 138 on 600. Alright, let's grab a conditional. 3 looks good enough. In a group of 20 dogs at obedience classes, 15 will stay when they're told, 9 will stand when they're told, and 2 will do neither. Let's go for a Venn diagram. Okay, I'm gonna, for question 3, I'll delete all that stuff. I'll delete. So question 3, here's my Venn diagram, and the 2 things we're discussing is stay and stand. Now there's a group of 20 dogs. Remember, when I write 20 outside the box, that's not official anything, that's just me reminding myself, don't forget to check your numbers at up to 20. 15 will stay when told. Well, that means 15 need to be in the stay circle, but is it 5, 10, 10, 5, 1, 14? I don't know. 9 will stand, that means put a total of 9 in the stand thing, but I don't know where. 2 will do neither. Okay, I can put that out there. Now what I know is all of this area out here is only 2. So what has to fit in the circle region? 18 has to fit. That add up to 20. But how many stayers are there? 15. How many standers are there? 9. So we've got a total there of 24, but I've only got space for 18. This is from last week. We find out the overlap. How many too many do I have? And here I've got 6 too many. I'm trying to fit 24 dogs where I've only got space for 18. That means 6 must have the ability to do both. When we counted the 15 stayers and the 9 standers, 6 dogs must have done both. That's why I've got 6 too many. Let's complete this and see if it works out. If 15 will stay, 15 minus 6, that means now there's 15 in the total in the stay circle. If 9 will stand and there's 6 there, that means put 3 there. So I've got 15 in the stay circle, I've got 9 in the stand circle. 9 plus 6, 15 plus 3 plus 2 is 20. Oh, he's done it. So our Venn diagram is sorted. Really, that was last week's work. But now let's check on the questions. They may not all be conditional. Let's find out. Question 3A is not conditional. It just says, if one dog is chosen at random, find the probability that it will both stay and stand. We're still talking about 20 dogs. What's the probability it will both stay and stand? 6 of them. 6 out of the 20. Alright, B, are you conditional? What's the probability that a dog at random will stay but not stand? That's not conditional. It's not saying I'm only talking about these dogs, these stay ones or the stand ones. No, stay but not stand is these 9 dogs here that will stay, but they're not like the 6 dogs that will stand. Stay but not stand, that's 9 out of the 20. Question C is asking me what's the probability that a dog at random will not stand. It's still not conditional. Not stand, well there's 9 that will stand. 20 minus 9, there must be 11 that wouldn't. These 9 and these 2. If 9 stand, 20 minus 9 must not. And then here's our conditional, and to me it's quite clear. It says, what's the probability of finding a dog at random that will stay, given that it will stand? Means, given we already know the dog can stand, and there's only 9 dogs that can stand, or will stand on order. So we're only talking about 9 dogs. Given that it will stand, given we're talking about these 9 dogs, how many of them will stay? 6 of them. 6 out of 9. So be careful for the conditionals. Somewhere in the question, like here, what's the probability of finding someone that does mathematics, given they have chosen science, I only talk about the science people. Apparently 48 people chose science. That's your new denominator. So be careful with your wording. Last one, let's do a table. Have I got a few more? Yeah, okay, there's a few more. I'll steal question 2. A survey of people in randomly selected court cases showed the following results. Actually, I said I was going to do one where I had to fill in some stuff. Oh, they're all filled in. God, I'm nice. Anyway, except for this isn't filled in. 50. The total of those two numbers is 50. The total across here is 50. By no accident, of course, there are 50 people in this survey. Now, and let's just look at the 4 main things. 3 people were innocent, yet they were convicted of a crime. Not good. 14 people were innocent and they were acquitted, found not guilty. Fantastic. 28 people were guilty and they were convicted. Good. 5 people were guilty, yet they were found not guilty. They were acquitted. So 3 and 5 are not good numbers, but the others are as they should be. Firstly, how many people surveyed? 50. How many people were acquitted? 14 innocents and 5 guilties. Who cares? 19 total were acquitted. How many were guilty? Again, who cares whether they were convicted or acquitted? How many were guilty? These 28 and these 5 were guilty. 33. What was the overall percentage of those convicted? The overall percentage of those convicted, well, is how many convicted people we had out of everyone. There were 31 convicted people out of 50, and I know I'm just going to cheat and say 31 on 50 is the same as 62 on 100, which is literally 62%. Or I could have gone to my calculator and said 31 divided by 50 and then times by 100 to make a percent. I would have got 62. What percentage, conditional, that's my conditional alert going off. What percentage of those convicted? We're only talking about convicted people. There's only 31 convicted people here. So of those, how many of those convicted were innocent? Well, 31 were convicted, 3 of them were innocent. Okay, I can't do that one in my head. It's 3 on 31, but it asks for a percent. So 3 divided by 31 times 100, my calculator's telling me is 9.677, blah, 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 blah. So 9.67, I'm going to go 9.7% to one decimal place. It was 9.67. Since a 6 was followed by a 5 or greater, I rounded it up to 9.7. Okay, here, if one of the people surveyed were chosen at random, what would be the probability that this person was wrongly convicted? Now, it's not conditional. It's still just one of the people of the overall survey were chosen at random. Wrongly convicted means they were convicted and they shouldn't have been. So how many people were convicted but they shouldn't have been? There were 31 convicted. 3 of them were convicted but they were innocent. That's 3. 3 people were wrongly convicted. They were innocent but they were convicted. 3 out of 250 people answers that question. Yep. The probability of finding... Oh, out of 250, where'd that come from? I hope I didn't say that anywhere else. I don't know where that came from. 3 out of the 50 people. Did it say percent? If one of them... Just said probability. It didn't say percent. 3 out of 50 will do. 6% if you want, but I don't need to do that. Then what have we got? If one of the people surveyed was chosen at random, what would be the probability that this person was wrongly acquitted? Wrongly acquitted means found not guilty, set free. So here we're saying how many guilty people were set free? How many guilty people were set free? 5 guilty were acquitted, 5 out of 50. The chances of finding someone at random that was wrongly acquitted is 5 out of 50. And then H. One of the convicted people is chosen at random. Conditional, one of the convicted people. There are only 31 convicted people, my denominator has changed. One of these 31 people are chosen at random. Find the probability this person is guilty. Well, 28 out of those 31. And again, it didn't say what percentage, so I'm fine with leaving you as a fraction. We're up to one of the innocent people is chosen at random. Great, conditional. There's only 17 innocent people in this whole thing. Right there. If one of those 17 is chosen at random, what's the probability this person was rightfully acquitted? Well, acquitted is for the innocent. 14 people were innocent and acquitted. That's what should happen. 14 out of 17 were rightfully acquitted. 3 out of 17 weren't. J. Reading J is 7. What's the probability of selecting a person who received an incorrect decision? It's not conditional. It's a person at random. We're out of 50 again. What's the probability of selecting a person who received an incorrect decision? Well, 2 incorrect decisions from what I can see. Innocent people being convicted and guilty people being acquitted. There are 8 people in total that got an incorrect decision, be it in their favour or against them. There were 8 people, 3 plus 5, who got the wrong decision. So it's 8 out of 50. Alright, I hope that was helpful, everyone, and hope you've enjoyed probability. Okay, bye.